so it's really, really nice. And then thank you to this big list of people on the screen here. So these are all people who I've worked with on this coffee stuff throughout. And well, I won't name check everybody, but I guess it's kind of interesting just to note the sort of diversity of the backgrounds of these people. So they're from all over the world, and also from, you know, vastly different disciplines. So there's academics here, so chemists, engineers, physicists. There's one lonely mathematician who's talking to you now, and there's baristas involved in this as well. So it really is quite kind of eclectic work. And yeah, so I thought just for funsies, I'd take, I don't know, 3 or 4 minutes just to say something about the kind of particular brand of maths that I do. So it's applied maths. And I guess the first thing to say is that in contrast to maybe the more pure mathematics, or the mathematics that people think of when you tell them you're a mathematician, applied maths is definitely not just algebra and theorems. So it's not just scary looking equations like this one. By the way, I'll be very impressed if anyone knows what equation that is. Tell me at the end if you do, and kudos to you if you recognize that one. So rather than just being about maths for maths' sake, it's really about kind of taking the technology of mathematics and going and applying it to solve what I would call real world problems. And I use the term real world in a very broad sense. So just to give you some idea, these are all examples of things that I've worked on personally. And if you ask other applied mathematicians, I'm sure they'd have even wider portfolio of things that they could tell you about. So I've gone and applied mathematics to batteries and solar cells, even avalanches. So like, you know, snow tumbling down mountains, messages springing about in the brains of squids, coffee brewing. So it really is kind of powerful. And for me, it's why it's so exciting. I don't know of many other disciplines where you really get to work on problems this varied. So I think it's what drew me to it, and it's what keeps me getting out of bed in the morning and going back to work thirsty. So it's a good thing to be involved with. So when I tell people this, a kind of reaction that I often get is, well, how can that be true? Like a battery and a cup of coffee and an avalanche couldn't be more different. Like, how is it possible that you can, you know, do all of these things using maths? And I guess the answer is that, well, equations aren't fussy. So the equations and the mathematics don't really care if you're thinking about a kind of electron racing around inside a battery, or if you're worrying about a caffeine molecule moving around inside a coffee machine or a coffee cup. The equations that dictate the motion of the two, they're not exactly the same, but they're at least similar. So you can, you know, apply the same sorts of mathematics to seemingly very different things. Okay, so with that said, yeah, I'll talk about coffee a little bit now. So first thing I should say, in case people don't know, is what an espresso is. So I'm going to be talking specifically about espresso, but much of what I say you could equally apply to other brewing methods. So I had a hunt around for a kind of definition of espresso, and there isn't really a good one, but there is kind of guidance given by these people called the Specialty Coffee Association. And so their definition, in inverted commas, of espresso is that you should, well, firstly, grind some coffee beans. That's the first thing. Second thing is you take about 15 grams of those coffee grounds and you put them in one of these things. This is called a basket in the trade. You then take the coffee and you tamp it into that basket. So that's what's going on here. You then apply something like 8 atmospheres of pressure to that basket. And the way you do that is you take this basket and you clamp it onto your espresso machine. You turn it on and you let it flow for something like 25 seconds. And if you've done all that correctly, what you should end up with is a little cup of coffee that weighs about 30 grams and hopefully tastes reasonable. So when I kind of started this, I didn't really know any more than anyone else really about making espresso. So the first thing I did was spend a long time talking to baristas, coffee brewers, just to try and understand the sorts of problems that they face. And what I kind of came away with was that they're trying to control all these different variables. So they're trying to wrangle the grind setting of the grinder that they're using, how much coffee they put in, how hard they tamp, the flow time and the water temperature. And they're trying to make these drinks that taste good. And these baristas, they always refer to this thing that I've got pictured here. So this is something called the Coffee Taster's Flavour Wheel. And it's basically a kind of universal dictionary that people in coffee use to try and characterize the different cups of coffee that they make. Honestly, my immediate reaction to this was that it was ridiculous and that it was pretentious, and how could you possibly need all these fancy words to describe coffee? And so I went away and started digging into the kind of science of coffee a little bit, the chemistry of coffee. And quite a long time ago, so back in the mid 60s, there was some chemical work done on coffee. People basically tried to catalog all the different chemicals that you can extract from coffee. And this is just a tiny snippet of the table. The full table contains about 2,000 different chemicals. And so once you realize this, it's kind of not so surprising that you need this variety of terms to try and describe the sensation that you get on your tongue from these different cups of coffee. Okay, so after that, I tried to understand what the kind of the big problems are in espresso. So, what are the issues that keep these baristas awake at night? What are they really worrying about? And there were two things that kept coming up over and over again. So one is that making espresso consistently is quite difficult. So these baristas would often talk about, they make 2 shots of coffee, one after the other. And to the best of their ability, they've done it in exactly the same way. Yet the 2 cups of coffee might taste quite different. And then another thing that came up over and over again is that espresso is somewhat wasteful method of brewing. So when you make espresso, you only get about 2/3 of the solubles out of the coffee, and the rest is wasted. So to try and summarize that, the 2 things that we could hopefully try and improve with some maths is the reproducibility of espresso and the efficiency with which it's made. So these are the 2 problems we're going to try and address. Okay, so one other piece of information I have to put into play before I go on to brewing is what happens when you grind coffee. So we got some friendly chemists who have a laser diffraction machine. We ground some coffees at different grind settings, and then we put the grounds into this laser diffraction machine. Basically what it does is you shine a light through the grounds, and from the pattern that the light makes, you can figure out what size the particles are in the grounds. And this is what we saw. So roughly speaking, you see 2 types of particle in in ground coffee, you see some very, very small ones, which are called fines. They're probably about 50 microns in diameter. So to give you some idea, that's probably a little bit wider than a human hair, 3 or 4 times wider than a human hair, or something like that. And then there's this other population of grounds which are much bigger. They're called boulders in the trade. For reasons I don't understand, baristas call them boulders. And when you adjust the setting on your grinder, 2 things happen at the same time. So as you grind finer, the boulders get smaller. So that's evidenced by the peak of this curve moving leftwards as the grind setting goes down. And the other thing that happens is that you get more fines. So the fines remain the same size as you adjust the grind setting, but you get more of them. And yeah, this information, it'll turn out that this is really important later. So just try and freeze this in your brains, and the importance of that will become clear in a few minutes. Okay, so now with the kind of prerequisites in place, we're in a position to try and start doing some maths. So here's a kind of cartoon of the inside of an espresso machine. So the big grey things are my boulders, the little grey things are the fines, and the blue stuff is the water or the coffee, if you prefer. And here's my kind of bullet point list of the essential things that we have to capture in a mathematical model. So the first thing we have to capture is how the liquid flows through this bed of coffee. So here's a kind of blue line that represents a kind of flow path for a particle of water. And then the other things we have to capture is what's happening to the coffee solubles. So when I say coffee solubles, I mean caffeine, various acids, these 2,000 different chemicals I was talking about a moment ago. I mean all of those things when I say solubles. So we have to describe, firstly, how the solubles get from inside of the grains to the surface of the grains. That's this yellow arrow. Then we have to describe how the solubles are dissolved at the surface of the grain and into the water. And then we have to figure out how the solubles move through the bed and ultimately come out of the bottom of the bed and end up in the cup, and then maybe in your mouth and in your belly afterwards. But we'll just concentrate on what happens in here. And so the showing you the full system of equations probably a little bit overwhelming. So I'm just going to show you a snippet. I'll show you a snippet of the equations that you need to describe the liquid flow. So that's these equations here. They're kind of famous. They're called the Neville Stokes equations. So some of you may have heard of them. They're kind of famous because there's a prize around them. There's a lot of money available if you can demonstrate there are solutions to these equations, or demonstrate there aren't solutions to these equations. So there's a bounty on their head if you can do certain things with them. And I highlight these because they're a great kind of exemplar of this this fact that I was mentioning earlier, that that mathematics is universal. So I'm going to use them to describe the flow of water through a coffee bed, which might look something like this. But equally, people use them for many other things. So if you go and talk to people who design Formula One cars, they're using these equations to figure out how air flows across a racing car. People who, meteorologists who forecast weather, they also use these equations. They're used in medical applications for people to model the flow of blood around a human body. And I could go on, but I shan't. So this is one ingredient in our model, and now I'm going to skip to the kind of end result. So this equation I've got on the screen now, this is, I would say, the centerpiece of our mathematical model. And again, it looks scary and intimidating, don't worry if you're feeling intimidated. You don't need to understand it fully to, appreciate the rest of what I'm going to say. But essentially what we can do is solve this equation on a computer and generate output like this. So here's a couple of graphs that I think are kind of interesting and informative. The left-hand one is a plot of what the model predicts the concentration of the coffee should be as it comes out the bottom of the machine versus time. So time is 0 when you switch the machine on. And then what you see shortly afterwards is a kind of spike in the coffee concentration. So initially the coffee comes out very strong, which is, I think, what we should expect. And then as the shot continues, the concentration of the coffee coming out gets weaker and weaker. And then I've got another plot on the right-hand side. So again, this is the concentration of coffee, but this time in the water flowing through the bed. So the top of the plot is the top of the machine. The bottom of the plot is the bottom of the machine. And this is what the concentration profile looks like inside the machine. And seeing this plot gives you a kind of hint at why a mathematical model is a useful thing to have, because in a real experiment, you can see the concentration of the coffee that comes out, but what you can't see is what's going on inside the machine. So it's only via the use of simulation that you get this extra insight that you just can't get from an experiment. Okay, so once we've devised our model, the next thing to do was to check whether it mimicked reality in any way. So we need to make sure that our theory is working in some sense. And so what we did was to go and compare the model, which is shown in pink crosses, versus some experiment, which is shown in black markers. And what this graph shows is, so it's grind setting on the horizontal axis. Larger means coarser, smaller means finer. And the vertical axis, you can basically think of this as coffee strength. So this is a very strong espresso, this is a very weak espresso. And so the experiments and the model both agreed, which was pleasing. And basically what this graph is saying is that if you grind your coffee finer, you get a stronger cup of coffee. And that kind of makes a lot of sense. We can explain why that is. So when you have a finer grind, you have several things going on at once. So one is you have more of the small particles I was talking about. Secondly, the big particles are also smaller. And both of these things mean it's easier to get at the coffee. So you can imagine if you have a small particle and you want to get the coffee out of the middle of the particle and into the water, the coffee only has to migrate a small way inside the particle until it can get out. Whereas if you've got large particles, they have to fight their way all the way from the middle of the particle all the way to the outside before they can get out. So it's easier to extract from small particles. And then there's another compounding effect that kind of enhances this, which is that when you've got lots of small particles, they pack together tightly. And that means that it's harder for the water to fight their way through the coffee bed. So the water stays in the coffee machine for longer, and it therefore has more of a chance to absorb the coffee on its way through the machine. So all three of these things together contribute towards this conclusion that a finer grind makes stronger coffee. So I don't think there's any surprises here. But the next thing that we did was where the surprise happened. So I've got the same graph here, but the data now extends into finer settings than it did before. And what the model says should happen is that as you continue to grind finer, the drinks get stronger and stronger. Unfortunately, reality had other ideas, and it did the exact opposite of that. So in reality, there's this kind of grind setting that once you go beyond it, or beyond it, I should say, the coffee actually starts getting weaker. It starts getting weaker, and it also starts getting more variable. So you'll notice there are several experimental data points here, and you'll notice that on the left-hand part of the plot, the experimental data points are further apart. So this is indicating that the shots are more variable over here. And we had a hard time explaining this, so we kind of scratched our heads for a while trying to figure out why this is. And essentially what we figured out is that when you pass this critical grind setting, suddenly the coffee bed becomes cloggable. And I've got a nice thought experiment to try and imagine why this cloggability suddenly happens. So imagine one of those like ball pits that you get in an adventure park, and fill that ball pit with beach balls. So those beach balls are the boulders in the coffee machine. And now at a fine grind setting, what you're going to do is you're going to pour just a few of those smaller balls that you would normally see in a ball pit. They're about kind of fist size. You're going to pour those balls amongst the beach balls. And if there are only a few of those smaller balls, when you try and flow water through this thing, it's quite easy for it to do so because there are big gaps between the beach balls, and the little balls get whooshed out of the way by the water. And so there's a very low chance of it clogging. But if you repeat the same thought experiment, but this time you pour on loads and loads of these little balls, being the fines, when you turn the water on and you try and flow water past this bed of balls, what happens is that the little ones, they all get pushed to the bottom, they all agglomerate together, and in doing so, they clog up bits of the bed. So they make it very hard for the water to flow through it. And this clogging is why the drink strength starts going down. So this is bad, right? So the bits of the bed that are clogged, you can't get the water to it, and therefore you can't get the coffee out of it. So this is why the drink strength drops off. And the clogging is kind of chaotic. So this is also why the variability is seen on this side of the picture. Now, it turns out when we asked baristas what grind setting do you actually use in practice, it turns out that they're in a grind setting down here. So they're actually usually in this clogged part of the regime. And so this clogging is, we think, the kind of main source, or one of the sources of inconsistency and inefficiency in the brewing. So we came up with a kind of bunch of strategies to try and alleviate this. And this is just one of them. So I'll try and talk you through this kind of cartoon of how you can improve your brewing. So essentially what we recommend that baristas do is they adjust their grind setting and they taste the drinks until they find what we call a tasty point. So the tasty point is this yellow thing here. And this is, as I said, in the clogged regime. So this is why their shots are hard to reproduce and they're not as efficient as they could be. And now what you do is you go and find the kind of most efficient point, which is this blue one. So it's the one that maximizes the drink strength. So this is efficient and you get the most out of your coffee that you can. Unfortunately, that drink doesn't taste good because it's too strong. So the way you compensate for that is you stay at this very, at the efficient grind setting, and you get less coffee out of the bed by letting the shot run for less time. And what that does is that moves the blue point down to this red point, which is now back in line with the tasty point again. So now you've got something that hopefully is tasty, but it's more concentrated than you had before. So what you can now do is top it up with a little bit of water to dilute it back down to something that people like. And now you've got a drink that is more efficient and is the same strength as what you decided was tasty. And so, some people kind of didn't believe this. They thought this was silly and would never work. And well, turns out it does work. So there's a cafe in Oregon that's been doing this for, well, since we told them about it, which is about 2 years ago. They've saved quite a lot of money. They're also wasting less coffee, which is good. So they're happy with this. And there's a cafe in Portsmouth which I've been helping dial in this strategy. They're also using it. They're not open at the moment because they're in lockdown, but hopefully we'll have another local example where you can go and see this being done. So I'll stop there. Just, well, I'll say two more things before I finish. So there's a couple of, well, there's more than 2 challenges that remain. So if there are any kind of budding applied mathematicians in the audience, there's plenty left for you to do. I haven't finished this problem by any means. So one thing that remains to do is to model this clogging. So at the moment, I've been a bit cowardly and just said you should avoid this clogging. I haven't really described thoroughly how it works. So there's definitely a challenge there to describe the clogging. And then the other thing that we haven't confronted, that I think is probably the most important thing to confront, is, so instead of just talking about drink strength, you should talk about the taste, because obviously, you know, you and I might disagree about what a good tasting coffee is. And so really the grand challenge is to do this in a way that everybody thinks tastes good. And that we certainly haven't conquered. So if you want to read more about this, this paper is out there already. It's open access, so you can go and download this and read it. And then there's another paper we're writing at the moment, which will be out soon. And I put this picture here just because I think it's cool. So it's like that's a picture of a boulder under a microscope. It's kind of weird looking, and I find it interesting, so I thought I'd show you. Yeah, that's all I had planned. So I hope you found that interesting, and yeah, happy to attempt to field any questions that you might have.
Jamie, thank you so much. That was absolutely fascinating.